Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Master of Science, Renewable Energy and Environment, MSCRWEE, Semester I, MRW-001 Energy Conversion, Block-1 Basic Concepts of Energy Conversion, Unit-1 Application of Engineering Science to Energy Conversion Systems. 1.1 Introduction. There are wide applications of engineering science to energy conversion systems. In an energy conversion system, energy can be found in four basic forms. These are electrical, mechanical, chemical, and thermal. On the basis of applications, each of the basic forms of energy can be converted to another form, and this process is reversible as shown in Figure 1.1. Look at the screen. The device that plays an important role for conversion of energy is called energy converter. It is a device inside which energy conversion takes place, where it takes one form of energy as input and deliver converted energy as output as shown in Figure 1.2. For example, motor, a device that converts electrical energy into mechanical energy to drive mechanical load. Look at the screen. In this unit, we shall discuss the fundamentals of various energy conversion processes and systems and their applications in different fields.
Objectives. After studying this unit, you should be able to know the fundamentals of various modes of energy conversion, describe the characteristics and performance of the energy conversion systems, and evaluate the applications of the systems in various fields. SAQ1. A. What is the need of energy conversion? B. What is the function of energy converter? 1.2 Energy and its conversion. This tributary is designed to help you understand what energy is and then to explain the ways by which energy can be converted, and how effectively, into forms that are technologically useful. The way the term energy is used, either colloquially or scientifically, often gives the impression that energy is a substance. We talk of energy flows, energy losses, energy inputs and outputs. This impression is misleading. Actually, energy is not a substance. It is an abstract concept which, like love or thought, has no physical existence. It is used to describe the equivalence of various physical processes. For example, you can produce motion through muscular effort, by burning a fuel in an engine, or through the unwinding of a spring. Part 1 then goes on to point out that various forms of energy and the ways they can be converted into one another. This determines their equivalence. It then describes the first important property of energy. In the law of conservation of energy, this law simply states that in any process which converts energy from one form to another, the total quantity of energy remains the same. The law of conservation of energy forms part of the science of thermodynamics, which is one of those abstract systems of explanations. Part 1 then goes on to point out that although no energy is actually lost in any conversion process, some may end up in a form which cannot be used for useful work. It is in this sense that we say that about 70 out of every 100 units of the energy in power station fuel are wasted. Only 30 units end up as electrical energy. The remainder is discharged to the surrounding as waste heat. This sort of comparison between the useful energy output and the total energy input leads to the concept of energy efficiency as a measure of the technical effectiveness of an energy conversion device. Not only does the useful output from an energy conversion process depend on the efficiency of the processes itself, it also depends on what is defined as useful output. For example, if only the output of electrical energy from a power station is regarded as useful, you can see from the figures above that the conversion efficiency is quite low, being 30%. However, if some of the heat output can also be utilized as well, the efficiency could be as high as 80%. As you know from the mainstream, this is the main consideration that led to thinking about combined heat and power stations. Sometimes it is not the quantity of energy which is important, but the rate at which it is used. Power is the technical term for rate of energy conversion. The final sections of Part 1 discuss power, and then the ways in which energy and power can be measured. They contain formulae and exercises to enable you to calculate quantities of energy and power in a variety of conversion processes. Part 2 of the tributary then takes a closer look at one particular energy conversion process which plays a key part in the generation of electricity. It is the conversion of heat energy to mechanical energy or work. Devices which do this, including car engines and steam engines in power stations, are called heat engine. Heat engines have inherent limitations to their conversion efficiency as a result of the second law of thermodynamics. Part 2 describes a simple form of this law, namely that heat energy cannot flow spontaneously from cooler to hotter substances. It then shows why this principle leads to the limited efficiency of heat energies, and how to calculate that limit. Part 3 of the tributary takes a closer look at the parts and operation of a conventional power station. Finally, in Part 4, we consider the modifications that can be made to a power station to optimize its energy efficiency as a combined heat and power station. So, in summary, by studying this tributary you will acquire the basic tools to help you to understand energy conversion principles and to calculate energy conversion efficiencies. You will also have a technical awareness of the means of implementing combined heat and power schemes to consider along with the economic, political and other aspects of the issue discussed in the mainstream. At the appropriate points in the mainstream, you will find links to this tributary. However, as you will have already noted in the study guide to the mainstream of this block, you may also read this tributary as a whole. Indeed, as the text progresses sequentially, this pattern of study would be quite appropriate. Audiovision Packet 6 and Television Program 8 are closely associated with Part 3 of this tributary. Audiovision Packet 6 is designed to help you through the calculations in SAQs. Television Program 8 takes you round a real power station and explores the practical reasons why it is not as efficient as theory predicts. 1.2.1 What is energy? As I said in the introduction, energy is an idea. It is an abstract, mental model used to explain certain observations. To illustrate it, I am going to consider some hypothetical situations which are intended to begin to link the scientific uses of the term energy to its common sense uses. I will introduce some of 3 forms in which energy occurs and the ways in which one form can be converted into another. If an object starts moving, then it's reasonable to assume that something's causing it to move. You know that it takes considerable effort to push a motor car along a flat road, so if you observe a car in motion, you presume that something is replacing your efforts. In scientific terms, it requires a force to make an object start to move, and when the object does move, the force does work on the object. Now let's consider the mechanical arrangement of figure 1.3. In this scheme, the car is attached to a sling by a rope which passes over a series of pulleys. Clearly you could make the car move by exerting sufficient pull on the rope. Your efforts, that is, the work you do, would cause the car to move. However, you could also make the car move by carrying a large rock to the top of the hill and placing it in the sling. The sling would then fall down the hill and pull the car along the road. The significance of this example is that your work was devoted to lifting the rock to the top of the hill, not to pulling the car. When the rock is at the top of the hill, it is somehow different from when it was at the bottom, since at the bottom of the hill it cannot cause the car to move. Somehow the rock at the top of the hill stored the work you did in lifting it there and was able to release this stored work as it descended. But the rock is not physically different at the top or at the bottom of the hill. It is not similar or larger, nor more or less heavy. Look at the screen. Clearly, one would like to explain this strange behavior, and this is where the idea of energy comes in. The idea is that in lifting the rock you lost some of your ability to do work, you got tired, and that the rock has gained some of this ability. In short, there is said to have been a transfer of energy. A name is given to the energy the rock has acquired, potential energy, sometimes called gravitational energy or gravitational potential energy. When you do work on the rock, lifting it up the hill, you increase the potential energy of the rock. This potential energy is stored by virtue of the new position of the rock relative to the center of the earth when the rock descends. Its potential energy decreased until, at the bottom of the hill, it returns to its initial value, so we can say that potential energy is associated with the position of an object, that is, how high up it is. But this is not the end of the story. The car attached to the rope is now in motion. If this car in motion were to collide with another, stationary car, the result would be that the second car would be set in motion. This means that work has been done on the second car to get it moving, and this work has been done by the first car attached to the rope. So the first car, when it was in motion, had gained the ability to do work, which is energy. This is another change in the ability to do work. The rock lost it in falling and the car attached to the rope has gained some of it when it started to move. There has been another transfer of energy of the rock has been transferred to the car, but the energy associated with the car is different from that of the rock. While the rock stores potential energy as a result of its high position, the energy transferred to the car is not stored because of the car's position but because the car is moving. This type of energy is called kinetic energy. This is another change in the ability to do work. The rock lost it in falling and the car attached to the rope has gained some of it when it started to move. There has been another transfer of energy of the rock has been transferred to the car, but the energy associated with the car is different from that of the rock. While the rock stores potential energy as a result of its high position, the energy transferred to the car is not stored because of the car's position but because the car is moving. This type of energy is called kinetic energy. Kinetic energy is the type of energy associated with movement. Not all the potential energy of the rock is transferred to the car. The rock itself is set in motion, it falls, and so the rock also gains kinetic energy. In fact, if you simply drop the rock from the top of the hill, rather than placing it in the sling, it would still lose all its potential energy by the time it reached the bottom, and the energy would all have been converted to kinetic energy of the rock itself. At the bottom of the hill, the rock might roll a considerable distance or it might cause a substantial amount of damage. So the story is as follows. The work done by you lifting the rock increases the potential energy of the rock. As the rock falls in the sling, its potential energy decreases, but the kinetic energy of the car attached to the rope end of the rock itself is increased. When the two cars collide, some of the kinetic energy of the first car is transferred to the second car. Thus the sequence of events is explained or described as a sequence of energy exchanges. So a way of thinking about energy is as the ability to do work. In the rather bizarre sequence of events I have described, you have seen how this ability, namely energy, can be acquired, stored and transformed. Although this example started from your doing work, most technologically significant energy exchanges are those that save human work. For example, in figure 1.4, the car is pulled along the road by the water-turning water wheel. The potential energy of the water on the top of the hill becomes kinetic energy of the water flowing under the water wheel. This in turn becomes kinetic energy of the rotating wheel, which is used to give kinetic energy to the car. An alternative method of using the energy of water is to allow it to drive a more modern version of the water wheel, a water turbine, which changes the energy of the water into kinetic energy of a rotating shaft. In turn, the rotating shaft can drive a generator, which produces another form of energy, electricity. This complete energy conversion system in the basis of hydroelectric power station and is illustrated schematically in figure 1.5. We deal with power stations, turbines and generators in Block 2 and Block 4. Look at the screen. Of course, electricity is used in a huge variety of ways, but to continue with my story, a particular way to use it could be to charge a battery and later use it to propel an electric vehicle, such as an electric milk float. To describe these latter processes in energy terms, we have to assume that the flow of electricity carries a flow of energy and that a battery can somehow store energy. The concept of energy is useful because it emphasizes the equivalence of apparently different situations. For instance, given the appropriate machinery, both a charged battery and a weight on the top of a hill can cause a car to move. It is this equivalence of the ability of different types of energy to perform useful work that accounts for the use of the work and concept of energy in every branch of technology. In order to understand the concept fully, you must be able to recognize the principal types of energy, to quantify each type, and to establish rules for the conversion of one type of energy to another. We start this task by considering in the next section the most useful forms of energy. 1.2.2 The main forms of energy. We can extend the idea of the equivalence of different types of energy to infer all of the principal forms of energy. You may be familiar with energy associated with position, potential energy, with motion, kinetic energy, and with the flow of electricity, electrical energy. I have listed below 6 more forms of energy. Heat energy. You have already been introduced to the idea that heat is also a form of energy. In many textbooks you will see this form of energy referred to as thermal energy. This can be demonstrated in the following way. Let's suppose that the potential energy of some water on the top of the hill has been converted to electricity and that the electricity has been used to boil a kettle of water. At this stage the energy, initially potential energy, has been used to heat water. Now suppose the hot water is poured over a glass bowl as illustrated in figure 1.6. The air in the bowl will increase in temperature and, as a result, will exert an increased pressure on the piston. That will cause the piston to rise, and therefore lift the weight on the top of the piston. But we have already established that lifting objects increases their potential energy, so the heat of the boiling water causes an increase in the potential energy of the weight. This is an energy sequence interrupted by a transfer of heat, potential energy to electrical energy to heat energy to potential energy. Since the heat has resulted in some useful work, it is reasonable to conclude that heat is a form of energy. The scheme of figure 1.6 may appear rather contrived, but, as you will see in Block 4, it is not all that far removed from the way the boiler in a power station works. Look at the screen. Strain energy. Work is also needed to compress a spring. When the compression is released, the spring can perform useful work. Thus a compressed spring can be viewed as an energy store. This stored energy can be used, for instance, to drive clockwork motors. In this case the energy is said to stored as strain energy. Chemical energy. The heat obtained by burning fuel, say, coal, oil or gas, has been converted from chemical energy stored in the fuel. You may be surprised to be told that a battery also stores energy as chemical energy and not as electricity. When a current is drawn from a battery, whether to light the bulb in your torch or to turn the starter on of any car, the chemical composition of the materials inside the battery changes. When car battery is recharged, other chemical changes take place. All this indicates that some substances store energy by the nature of their chemical composition. This stored energy is called chemical energy. Explosives, for example, are substances whose chemical energy can be very rapidly converted into other forms of energy. Potential energy, strain energy and chemical energy are forms of energy that can be stored. You can leave energy stored in these forms and come back here later and make use of it. You can also carry energy about from place to place as strain or chemical energy. Kinetic energy and heat energy can be used as temporary stores of energy. For instance, a rotating flywheel or a tank of hot water can be used to store energy, but in a while you would find that the flywheel had slowed down or the tank had gone. These forms of energy are more useful as means of transporting energy rather than of storing it. Electrical energy can only be used to transport energy from one place to another more or less instantaneously. As soon as the current stops, the energy flow stops. There are two other forms of energy that may also be referred as transfer energy. These are sound and light. Sound energy. As you know, a loudspeaker converts electrical energy into sound. At high volume, this sound can make things vibrate, that is, give them kinetic energy. Chains of energy transfers like this show that sound is a link in the chain and that sound carries energy. You must have heard the name of famous musician Tansen, who had the capability to convert sound energy to heat energy for burning diyas. Light energy. An electrical light bulb converts electrical energy into light, and a photoelectric cell is a device that converts light into electricity. These examples and the fact that the sun's rays are able to heat objects show that light is also a means of transferring energy. Nuclear energy. There is one other important form of energy, nuclear energy. You know from ET 105a, electricity, that all matter is composed of atoms, which can be pictured, modeled, as a nucleus surrounded by electrons. In certain types of atom, the nucleus undergoes changes that release energy. This energy is called nuclear energy. Nuclear energy is used in nuclear power stations and also in nuclear weapons, as well as in a variety of medical and other applications. I shall not be going into the details energy in the tributary. So far, then, you have met 9 forms of energy: potential, kinetic, electrical, heat, strain, chemical, sound, light and nuclear. Clearly, there are lots of naturally occurring forms of energy that have the capacity to do work and which, therefore, can be used as substitute for human physical efforts: sunlight, wind, kinetic energy, water in a reservoir, the chemical energy in coal and oil, the nuclear energy in uranium, and so on. These not only save personal effort but they are also much more powerful than the efforts of individual people. They therefore enable people to accomplish all sorts of things that would otherwise be impossible. As a simple example, if you wanted to replace the fuel energy of a fairly ordinary electrical power station with human energy, you would need 1 million superfit athletes going flat out. A great deal of technology is devoted to harnessing these different forms of energy, and this is one of the main reasons why a block of this course is concerned with energy. 1.2.3 The unit of energy. Each of the forms of energy can be converted into any of the others, so to measure energy we need only a single unit of measurement. The unit of energy used in the SI is based on the equivalence of all forms of energy to work, movement against a force. The work W done is simply the force F exerted on the object multiplied by the distance t moved. In the form of an equation, this is work equals force into distance, or W equals Fd. 1.1. In the SI, distance is measured in meters, m, and force is measured in newtons, n. So, EQ 1.1 indicate that the unit of work is the Newton meter, nanometer, and it is given the special name of the joule, J. This, then, is also the unit of the energy. 1.2.4 Energy conversion. In the ultimate energy conversion machine shown in figure 1.7, most of the types of energy discussed are involved in the storage and transmission of work done. It is not meant to be taken too seriously because some of the energy transfers are out of all proportion to others, and some of the devices shown can run continuously, like the electric generator, whereas others, like the compressed spring or the falling weight, can only transfer a limited amount of energy. Look at the screen. Nevertheless, it should help you to visualize how physical effort can be transformed into different types of energy and ultimately do work. Although 9 forms of energy are discussed in section 1.2.2, there are really only 5 major categories of energy of technological importance, namely mechanical, including kinetic energy, potential energy, strain energy and sound; electromagnetic, including electrical energy, light and the energy of magnetic fields; thermodynamic, heat in all forms; chemical, basically, the energy which binds atoms together to form molecules; nuclear, energy obtained from processes that occur in the nuclei of atoms. Between them, these 5 categories give 25 possible conversions, of which 16 are the basis of important technologies. These are shown with examples in the matrix of table 1.1, which also indicates an important general feature of energy conversions. Transformations can occur from any form of energy to heat. Table 1.1. The major types of energy conversion with some examples. Look at the screen. 1.3 Energy conversion and efficiency. 1.3.1 Conversion of energy. Throughout the last 3 sections we have described transformations from one form of energy to another. We did not then consider whether all the energy was converted from its first form to its second, or whether, in fact, the total quantity of energy was the same before or after the transformation. The important question is, can all the energy in one form be converted into a Desired, useful form? The short answer to the question is that in practice only some of the stored energy can be recovered in the form it is wanted. The rest is converted into other forms that are not wanted. The reason for this is that any machine that converts from one form to another will in fact have several energy outputs, not just the output desired. For example, a water wheel won't convert all the potential energy of the water into kinetic energy of a rotating shaft. The devices shown in figures 1.4 and 1.5 for instance. What other energy outputs would you expect? If you have ever visited an old water mill, you will recall that the most obvious additional outputs are the sound energy and kinetic energy of the water after it leaves the wheel. In addition, you may also think of the friction between the axle and its bearings, which will lead to a heat output, and the cracking and grinding, which will give a sound output. Thus, if you measured the initial potential energy of the water and the final work done by the wheel, you would conclude that there was less output of work than input of potential energy. This brings us to a principle that scientists use to construct models of how energy behaves in the physical world. It is one of the principles that is mentioned in the introduction, and is often called the law of conservation of energy. The most general form of this law is that energy can only be transformed from one form to another without gain or loss. This means that in a closed system, that is, one in which no energy crosses the boundary in either direction, the total amount of energy, potential energy plus kinetic energy plus heat energy plus all other kinds of energy never changes, however much the distribution between the various kinds may change. In an open system, such as a power station, the law of conservation of energy implies that the total energy input to the system, the coal or oil for a power station, for instance, and any work that is done on them from outside, must be exactly equal to the total energy output. This law has been tested by ingenious experiments many times and has come to hold a very important place in science and technology. I shall be making extensive use of it in the remainder of this text. To apply it correctly, we have to be careful to include all the inputs and outputs. This law has been tested by ingenious experiments many times and has come to hold a very important place in science and technology. I shall be making extensive use of it in the remainder of this text. To apply it correctly, we have to be careful to include all the inputs and outputs. For instance, when we consider a power station or a domestic heating system, we must remember that the heat energy that goes up the chimney is an output, even though it is not useful. 1.3.2 The effective energy conversion. So far we have seen that energy can occur in many forms, and that there are a variety of processes, burning, batteries, motors, solar cells, etc., in which one form of energy can be transformed into another. We have also seen, from the law of conservation of energy, that the total quantity of energy at the end of a conversion process is the same as that before it started. Alternatively put, the total energy input to a conversion process is equal to the total of the energy outputs from that process. In most energy conversion processes you are likely to come across, the output energy appears in more than one form. Thus in a car, the chemical energy in the petrol is transformed not only into the kinetic energy of the forward motion of the car, but also into heat in the exhaust gases and in the air which cools the engine and in the tires, and into the sound energy of the engine. In an electric motor, the electrical energy of the shaft and whatever is connected to it, but also into heat energy of the coils of the motor and of its bearings due to friction. Most man-made energy conversion processes are designed for a purpose. In the two examples just described, the purpose is to produce kinetic energy. Any of the forms of energy other than those for which the process was intended are considered to be wasted. Much ingenuity and careful design effort have gone into understanding energy conversion processes to ensure that as much as possible of the input energy ends up in the desired form, and as little as possible in forms considered as waste. One way of assessing the success of this effort is to calculate the ratio of the useful energy output to the total energy input. This is called the efficiency of the conversion process. Efficiency of conversion equals useful energy output upon total energy input. The total energy flows in the process is described by the law of conservation of energy as total energy input equals useful energy output plus waste energy, or, using the symbol IN for total input, E1 for useful energy output and E2 for waste energy. A in equals E1 plus E2, 1.2. The symbol most often used for efficiency in ether, the Greek letter ether, pronounced ether. Thus, in symbols, conversion efficiency is given by ether equals E1 upon A in equals A in minus E2 upon A in equals 1 minus E2 upon A in. 1.3. A pictorial way of representing the same information is the block diagram, in which the conversion device is represented as a box, and the energy flows as arrows. Figure 1.8. EQ, E3, shows that for any conversion process to be efficient, ether approximately equals 1, E2 should be as small as possible. Look at the screen. As you can see from this example, the conversion efficiency of a device is not necessarily an intrinsic or inherent property of that device. It depends upon which of the outputs are considered to be useful. This point will appear again later in this tributary when we look at combined heat and power, CHP stations. In a CHP station, much of the heat energy which would be considered as waste in a conventional power station is put to good use. Heating homes, shops, etc. Thus the overall conversion efficiency can be greatly increased over that of a conventional station. We started this section by considering the energy conversion in a car and in an electric motor. The best electric motors have conversion efficiencies of 90 to 95%. On the other hand, a car engine is doing very well if it can reach an efficiency level of 20%. As another example, consider the steel ball in figure 1.11. It is released at a height h. When it reaches the bottom, its potential energy has been converted into kinetic energy. It will then roll upward again, stopping at very nearly the height at which it started. Thus it regains nearly all the potential energy it had at the start. The transformations from potential to kinetic to potential energy must have conversion efficiencies near to 100%. Again, by way of contrast, a modern conventional electric power station may have a conversion efficiency of the order 35% or so. Look at the screen. These four examples illustrate the great divide that exists among energy conversion processes, those which can achieve conversion efficiencies approaching L100%, if enough care is taken to reduce waste energy outputs, and those for which conversion efficiencies are inherently low. The low efficiency processes include all forms of heat engines, that is, devices which convert energy in the form of heat into work or kinetic energy. They thus include petrol, diesel, and steam engines, or the steam turbines which drive the generators in a power station. In part 2 of this tributary we shall look at heat engines in more detail. We shall consider the physical reasons why the conversion efficiencies of many heat engines are inherently limited to between 30 to 60%. It is certainly not simply a matter of poor design. 1.4 POWER and quantification. 1.4.1 Power. Although energy is used in everyday speech in a number of different ways, the contusion is negligible as compared to the meaning and uses of the word power. Power is often misused as though it were interchangeable with energy. It is also used loosely to mean electrical power, as in power stations. Nonetheless, in science and technology, power has just one meaning. It is the rate at which energy is transformed from one form to another. The average power of a machine, or process, is the total energy converted divided by the time taken. Power equals energy converted upon time, 0.1.5. Or in symbols P equals A upon T, 0.1.6. Where P is the power and A is the energy converted in time T. The total energy transferred can be calculated by multiplying the average power by the time taken. In symbols this is A equals PT. Most machines are power limited. In other words, they can handle N indefinite amount of energy but at no faster than a certain rate. This is the significance of power in technology. Similarly, the performance of a motor car is more often described in terms of maximum speed, equivalent to power, and not in terms of the total distance, equivalent to energy, it can travel, which in any case is not known beforehand. Some simple examples of the production and consumption of energy can illustrate the significance of power. The power rating of a device is the amount of energy it transforms per second, that is, energy divided by time. Thus a single bar electric fire with a power rating of L000 watts transforms 1000 joules of electrical energy to heat energy every second. In 3 seconds this fire will give an output of 3000 joules of heat. Similarly, a 3-bar electric fire with a power rating of 3000 watts will give out 3000 joules of heat energy in 1 second. So 1 bar electric fire can produce the same amount of heat energy as 3-bar fire, but it takes 3 times as long. However, the usefulness of the two fires in raising the temperature of a room is not the same. You will recall from the definition of heat that temperature is a measure of how hot an object is, and that this is not the same as heat. The same quantity of heat energy from, say, a fire, can make an object with a small heat capacity very hot, that is to say, raise its temperature a lot, but will only slightly raise the temperature of an object with a large heat capacity. Not only will the 3-bar fire warm the room more quickly, it will also raise the room temperature more than the 1-bar fire. The point is that the heat loss from a room is a number of joules of heat per second, so although you can put the same energy into the room by leaving the 1-bar fire on 3 times as long, in this longer period the room will have lost more heat. Thus, although you can get the same amount of energy from both fires, their usefulness as room heaters is reflected in their power rating. A schematic diagram of a hydroelectric power station was given in Figure 1.5. It could also be called a hydroelectric energy station since its function is to transform the potential energy of water, hydro, to electricity. But, in practice, it is the power available from the station that is more technologically significant than the energy available from the station. The total energy stored in the water behind the dam may be measured in billions of joules, but it cannot all be converted to electricity in 1 second. The flow of water out of the dam carries a flow of kinetic energy, which is the power available. The faster the flow, the more kinetic energy arrives per second, so the more electrical power is produced. If the water flow is very small, then so too will be the electrical power output. If the power output is insufficient to heat all the houses connected to the electricity supply, it is not much of a consolation to tell the consumers to wait longer until the necessary amount of energy has been covered. They will ask for a bigger power station, not a bigger energy station. The efficiency of an energy conversion process can sometimes be expressed in terms of power ratios instead of energy ratios. For example, during any period of time when the power of the inputs and outputs is constant, the energy ratio and power ratios will be the same. Useful energy output upon total energy input equals useful power output upon total power input. For such a period we can find the efficiency as ether equals useful power output upon total power input. 1.4.2 units in scale. At the last count there were at least 11 units in common use for power and energy measurement, but, as you will appreciate by now, the International System of Units, SI, being used in the course. You have already met some SI units, such as the Newton, N, the Watt, W, and the Joule, J. However, if you read elsewhere about energy and its uses, you will inevitably come across the many other units of measurement. This section conveys two things. The first is the relative sizes of different quantities of energy commonly met. The second is the general principle of approaching energy equations and formulae. The reason for doing this is that, in general, it is more important to have a feel for size and an approach to quantifying things rather than an encyclopedic memory. I have tried to Choose examples that you will find helpful in general as well as for your study of this tributary in the mainstream. To appreciate the significance of energy in technology, it is essential to appreciate the scale of energy used. It is important to know roughly how much energy there is in 1 ton of coal or a fully charged car battery. To appreciate as, say, 1 ton of uranium nuclear fuel, these problems can be put into focus by relating them either to your own energy capacity or to your domestic requirements. For example, how much chemical energy in petrol has to be supplied to a mechanical cultivator in order to dig the garden? Or, how much energy can be stored in a car battery? But, before answering these questions, you have to know how to put numbers to the quantities as shown in the following example. Example 1.3. The energy gained by an object is equal to the work done on the object. Hence, if an object requires a force of 10 N to lift it, and the object is lifted through 1 meter, the work done is force x distance, and equals 10 Newton meters or 10 J. As a result, it can be said that the potential energy of the object has been increased by 10 J. Example 1.4. How quickly would you have to raise 5 apples, exerting In each, by 1 meter in order to increase their potential energy at a rate of 10 W? Solution. The task requires the conversion of 5 N times 1 meter equals 5 J of your energy. To do at a rate of 10 W, you must lift the apples in half a second, i.e., 10 W times 0.5 S equals 5 J. 2. How much would the electricity cost to boil 100 kettlefuls of cold? In this kettle, if the electricity board charges Rs 1.50 per unit, i.e., per kilowatt hour, you may wish to use SAQ5 to provide a mental image for the approximate size of a joule, the energy needed to raise an apple by 1 meter. Clearly, 1 J is not a large quantity of energy on a human scale, and on an industrial scale, it is very small. For a large industrial crane of press, a typical task might require conversion of millions of joules. Thus, it is more usual to express industrial requirements in megajoules, symbol, mj, 1 megajoule equals 1000 OOJ, or 10 power 6 J. As you know, the SI unit of power is watt. A power of 1 watt, 1 W, represents the transfer of 1 joule per second, 1 Js power minus 1. What do you think is the power rating of a car, or the power rating of Concorde? How much energy is there in 1 gallon of petrol or 1 ton of coal? These are questions of size which only frequent use of the numbers and concepts can make familiar. We remember 2 figures. The energy in 1 gallon of petrol or fuel oil is 50 kWh, 180 megajoules, and the energy in 1 ton of coal is 8000 kWh, 28,800 megajoules. These are not exact numbers, since it actually depends on the grade of petrol or the type of coal, but they are accurate enough to estimate other quantities, such as the power rating of a motor car. Example 1.6. Estimate the average power rating of a motor car which, when traveling at 30 km p.h., has a petrol consumption of 30 km per gallon. Solution. 1 gallon of petrol contains 50 kWh of energy. The car consumes this in traveling 30 miles at an average speed of 30 km/h, 30 km is covered in 1 hour. Therefore, the consumption of 1 gallon of petrol containing 50 kWh of energy in IR corresponds to a power rating consumption of 50 kilowatts. You are listening to this audiobook on Audio Learn IGNOU 1.4.3 Energy Calculations. You now know the units for energy and power, and methods for calculating power from energy and vice versa. You should also be getting some idea of the size of the numbers involved, from the mainstream as well as from the examples here. But we have not yet considered how to calculate quantities of energy from mechanical, electrical and chemical data. This will be done in this section. Let us consider the following equation. Work equals force times distance. 1.7. To set something in motion, a force has to be great enough to overcome friction, rubbing, between the moving object and what it is moving on, or against. Some of the force is taken up with overcoming friction and remainder when causes the object to accelerate, to go faster and faster. In fact, force is defined in terms of the acceleration it produces on an object. In case you are a bit uncertain about the meaning of acceleration, we will explain it a bit more carefully. As you know, speed is the rate of change of position and is expressed as a distance divided by a time. The SI unit of speed is the meter per second, ms⁻⁻1. Acceleration is the rate of change of speed. And so acceleration is expressed as a speed divided by time. The SI unit of acceleration is therefore the meter per second, ms⁻². You will also hear this read as meter per second squared. For example, if the speed of a car increased from 13 meters s⁻⁻1, about 30 meters p.h., to 20 meters s1, about 45 meters p.h. in 5s, the car's average acceleration over the period is 20 minus 13 into ms⁻⁻1 upon 5 equals 1.4 milliseconds power minus 2. The relation between the force F acting on an object of mass m and the acceleration are produced by the force is force equals mass times acceleration. F equals ma. In the SI unit, you can see that 1 N equals 1 kilogram times 1 millisecond power minus 2 equals 1 kilogram ms power minus 2. Weight is the force exerted on a mass in the Earth's gravitational field, which accelerates the mass, if it is allowed to fall freely. So, the force F, that is, the weight of an object, is its mass m times the acceleration g due to gravity. F equals mg. You know that force is related to work by the distance over which it acts. The work W done by a force F in moving a distance d is W equals Fd, 1.8. You also know that the energy change A produced is defined as the work done. So, when a force of 1 Newton moves an object through 1 meter, the work done, which is equal to the energy change, is 1 joule. 1 J equals 1 N times 1 meter. Equals 1 kilogram ms power minus 2 times 1 meter. Equals 1 kilogram m square. S power minus 2. Let's consider the potential energy A, of the rock in figure 1.3 again. If we call the mass of the rock m, its weight is force mg. When you carried the rock on the rock, raising it to a height h. Now using EQ, 1.7, for the work done, we get work done equals force times distance, equals mg times h, equals mgh. But the work done, by you, is the gain in potential energy of the rock, so we can write AP equals mgh, 1.9. When the rock is in the sling it exerts a force mg, its weight, on the rope n. As it falls the distance h down the hill, it loses potential energy, which is converted into other forms of energy, such as kinetic energy. The quantity of kinetic energy depends on the mass m of the object in motion and on its speed v. In fact, the kinetic energy A is proportional to the speed squared, and the equation is A equals half mv square, 1.10. So if we could say if all of the potential energy is converted to motion, then A equals 1.11. 1.5 modes of energy conversion. There are various modes of energy conversion. There are some energy conversion processes that use only one stage. Again, there are some other energy conversion processes that use many stages. On the basis of number of stages used, the energy conversion processes can be classified mainly into two categories. Hence, two basic modes of energy conversion are 1. Multi-stage energy conversion, and 2. Direct or single-stage energy conversion. These are further described in the following sections. 1.6 Multi-stage energy conversion. In this mode of energy conversion, the final energy output is obtained when the primary energy input undergoes many stages of energy conversion as shown in figure 1.14. In a coal-fired thermal power plant, the chemical energy of coal is finally converted into electrical energy when it undergoes 4 stages of energy conversion, i.e., from chemical energy to thermal energy to kinetic energy to mechanical energy, and mechanical energy to electrical as shown in figure 1.14. Look at the screen. There are many processes of multi-stage energy conversion. But, in this course, we shall discuss only two important processes which are widely used. These are electromechanical energy conversion and auto fuel energy conversion. 1.6.1 Electromechanical energy conversion. Electromechanical energy conversion involves the interchange of energy between electrical system and mechanical system through the medium of a coupling field as shown in figure 1.15. The process is essentially reversible, except for a small amount which is lost as heat energy. Look at the screen. The device that plays an important role for electromechanical energy conversion is called electric machine. We shall discuss the fundamentals of the electric machines in the following sections.
Electric machines. These are electro-mechanical devices that convert electric energy into mechanical energy and vice versa. Each electric machine is associated with two types of circuits, i.e., electric circuit and magnetic circuit. Construction. An electric machine has mainly three parts. These are 1. Stator, 2. Rotor, and 3. Windings. 1. Stator. It acts as the outer cover of the whole machine to protect it from rain, dust, heat and bad climates. The main function of this part is to provide path for magnetic flux. It is the static part of the electric machine. 2. Rotor. It is the rotating part of the machine. 3. Windings. Two types of windings are used in electric machine. These are 1. Field winding and 2. Armature winding. 1. Field winding. It is the winding that is used to produce magnetic field. 2. Armature winding. It is the winding in which EMF is induced. Classification of electric machines. On the basis of mode of energy conversion, electric machines can be classified as 1. Generators and 2. Motors. 1. Generators. These are the devices that converts mechanical energy into electrical energy. See figure 1.16. Look at the screen. Working principle. A generator works on the principle that when a conductor is moved in a magnetic field, an EMF is induced in it according to the Faraday's law of electromagnetic induction. Separately excited generator. In this type of generator, the field winding is excited by a separator D.C. source, for example, a battery. A schematic diagram is shown in figure 1.17. Look at the screen. Self-excited generator. In this type of generator, the field winding is excited by a part of the current generated by itself. On the basis of the connection of the field winding, self-excited generator can be classified as A. Series generator, B. Shunt generator, and C. Compound generator. A. Series generator. In this type of generator, the field winding is connected in series with a armature as shown in figure 1.18. Look at the screen. B. Shunt generator. In this type of generator, the field winding is connected across the armature as shown in figure 1.19. Look at the screen. C. Compound generator. In this type of generator, the field winding is divided into two parts. One part is connected in series and another part is connected across the armature as shown in figure 1.20. Look at the screen. Generator EMF. When the armature of a DC generator starts rotating, the EMF induced across it is given by A equals ZNOP upon 60A. 1.14, where Z equals total number of conductors, N equals speed in RPM, O equals flux, pole, P equals no of poles, and A equals no of parallel paths. A equals P for lap wound generator, A equals 2 for wave wound generator. Conversion efficiency. The efficiency of any device is given by Ether equals output power in kW upon input power in kW. 1.15. Let us consider a DC generator that is used to deliver a current at terminal voltage V to a load as shown in figure 1.21. Look at the screen. AC generator. AC generators are also called alternators. They operate on the same fundamental principle of electromagnetic induction. In their case, standard construction consists of armature windings mounted on a stationary element called stator and field windings on a rotating element called rotor. On the basis of number of phases used, alternators are classified as single-phase alternator and three-phase alternator. Motors. These are the machines that convert electrical energy into mechanical energy as shown in figure 1.22. Look at the screen. Working principle. The action of the motor is based on the principle that when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force whose direction is given by Fleming's left-hand rule. Classification. Based on the type of signal used, the motors can be classified mainly into two categories, i.e., DC motors and AC motors. DC motors. These are used to work on direct voltage and current. Separately excited motor. In this type of motor, the field winding of the machine is excited by a separate DC source as shown in figure 1.23. Look at the screen. Self-excited motor. In this type of motor, the field winding is excited by a part of the current drawn from the source by itself. On the basis of the nature of the connection of field winding, the self-excited motors can be classified into three categories, i.e., series motor, shunt motor and compound motor. A. Series motor. In this type of motor, the field winding is connected in series with the armature as shown in figure 1.24. Application. Series motors are used in railway traction. B. Shunt motor. In this type of motor the field winding is connected across the armature of the motor as shown in figure 1.25. Application. Shunt motors are used for driving shafting, machine tools, lathes, woodworking machines etc. C. Compound motor. In this type of motor, there are series and shunt field windings as shown in figure 1.26. Look at the screen. Application. Compound motors are used to drive rolling mills, etc. Power balance, torque and efficiency. When an electrical machine is used to work as a motor, it takes electrical power and converts it into mechanical energy to drive a load. As shown in figure 1.27. Look at the screen. Power balance. Electrical power, net, equals mechanical power, gross. But, electrical power, net, equals electrical power, gross, electrical losses. And mechanical power, gross, equals mechanical power, net, plus rotational losses, etc. Application. Synchronous motor can be used for conversion of AC power to DC power. Asynchronous motor. It has variable speed. Induction motor is an example of this type of motor. Induction motor. It is just like a transformer with stator winding forming primary and rotor winding forming rotating secondary. 1. Single-phase induction motor. It has only one winding. It is not self-starting. To make it self-starting, an auxiliary winding is needed as shown figure 1.28. Single-phase induction motors are also called fractional horsepower motors because they have the capacity less than 1 horsepower. Applications. Single-phase induction motors are widely factories and domestic buildings. They are used in ceiling fans, sewing machines, vacuum cleaners, printing machines, etc. 2. Three-phase induction motor. It has three windings in stator to draw current from the three-phase source. It has wide range of speed but it is not self-starting. There are two types of three-phase induction motors, i.e., squirrel cage type induction motors and slip ring induction motors. Slip and frequency of rotor current of induction motor. When the three-phase windings of the stator are excited, the stator produces a field which runs at synchronous speed given by EQ 1.28. 1.6.2 Auto fuel energy conversion. In this type of multi-stage energy conversion, the chemical energy of auto fuels like diesel and petrol is converted initially into thermal energy. This thermal energy is converted into kinetic energy and then it is finally converted into mechanical energy as shown in figure 1.29. Look at the screen. The device that takes an important part in this type of energy conversion is the automobile engine. Automobile engine. It is a device that converts kinetic energy of hot fluid into mechanical energy as shown in figure 1.30. Classification. I. On the basis of the nature of fuel used, the automobile engine can be classified mainly into two categories, i.e. A. Diesel engine, and B. Petrol engine. A. Diesel engine. It makes use of the energy of diesel fuel. It is generally used for heavy automobiles. B. Petrol engine. It makes use of the energy of petrol fuel. It is used for light automobiles. E. On the basis of the number of cycles of operation, the automobile engines can also be classified as A. 4-stroke engine, and B. 2-stroke engine. A. 4-stroke engine. The complete cycle of operations in this type of engine is completed in 4 strokes of the piston. These strokes are suction, compression, power and exhaust as shown in figure 1.31. Look at the screen. A 4-stroke engine has greater piston speed than a 2-stroke engine using crankcase compression. Also, it has a wider variation in speed and load, cooler pistons, common crank case in multi-cylinder construction, no fuel loss during exhaust, higher mechanical efficiency and lower specific fuel consumption. B. 2-stroke engine. In this type of engine, the complete cycle of operations is completed in 2 strokes of the piston or in 1 revolution of the crankshaft as shown in figure 1.32. A 2-stroke engine has low cost and it gives for same speed and piston displacement from 50% to 80% greater power output. That is given by a 4-stroke cycle engine. 3. On the basis of the number of cylinders used, the automobile engines can be classified as A. Single-cylinder engine, B. 2-cylinder engine, and C. 4-cylinder engine. Expressions for mechanical efficiency, thermal efficiency and specific fuel consumption. 1.7 Direct energy conversion. In direct energy conversion, there is no intermediate stage and energy conversion takes place with one stage only. There are various modes of direct energy conversion. Some of the important methods of direct energy conversion are the following. 1. Electro-chemical energy conversion. 2. Thermoelectric energy conversion. 3. Photo-electric energy conversion. A brief description of these 3 conversion systems is given in the following sections. 1.7.1 Electro-chemical energy conversion. In this type of energy conversion, chemical energy is converted to electrical energy or electrical energy is converted to chemical energy as shown in figure 1.33a. This process is reversible and isothermal. The device in which this type of energy conversion takes place cell has very high conversion efficiency. Fuel cell. A fuel cell is an electrochemical device in which the chemical energy of a fuel is converted into electricity. Fuel cells, if used in conventional method of converting fuel into electrical energy, may increase overall efficiency of conversion cycle, as shown in figures 1.33b and 1.33c. It is seen that in first case, the useful output is W, whereas in the second case, it is ether Q plus 1n W, where ether is the efficiency of the fuel cell. Fuel cells can be classified in more than one way. Based on their operating temperature, they are classified as low temperature, 25. 100 degrees Celsius, medium temperature, 100 to 500 degrees Celsius, high temperature, 500. 1000 degrees Celsius and very high temperature, greater than 1000 degrees Celsius. Another method of classification is based on the electrolyte used, i.e. aqueous, non-aqueous and solid. Fuel cells are also classified based on the physical state of the fuel, i.e. gas, hydrogen, lower hydrocarbons, liquid, alcohols, hydrazine, higher hydrocarbon, and solid, metals. The fuels mainly used in fuel cells are hydrogen, fossil fuel, hydrocarbon fuel, alcohol fuel and hydrazine fuel. When two output terminals of the fuel cell are connected to a load, then it supplies electric current. Thus the chemical energy is converted to electrical energy as shown in figure 1.34a. Look at the screen. Alternatively, if the two terminals of the above cell are connected to a voltage source to charge it, then electrical energy is converted to chemical energy as shown in figure 1.34b. Look at the screen. 1.7.2 Thermo, electrical energy conversion. In this type of energy conversion, the thermal energy is converted directly to electrical energy as shown in figure 1.35. The device that takes part in this type of energy conversion is called a thermocouple. Look at the screen. The thermocouple works on the principle that when the junction of two dissimilar materials is heated, then the voltage appears across the output terminals of the thermocouple. Thus, the thermal energy is converted to electrical energy by thermocouple. 1.7.3 Photo, electric energy conversion. In this process of energy conversion, the incident radiation is converted into electrical energy as shown in figure 1.36a. The incident radiation can be in the form of electromagnetic radiation, i.e., X-rays, gamma rays, light rays, or particle radiation, e.g., beta particles, alpha particles, etc. The device that is used for this type of energy conversion is called photovoltaic cell or solar cell. It is made of semi-conductor material. When the incident radiation strikes the junction of the semi-conductor material, voltage appears across the terminals of the cell. Thus, the energy of photon is converted into electrical energy. One of the most promising application of solar cells for electric power generation was in spacecraft where silicon solar cells were used. Solar cells would be utilized for small or large power plants. Solar cells are now being used for lighting purposes in remote rural areas, for operating irrigation pumps, for petrol pumps, rail, road signals, etc. Solar cell operated cars have also been tested in European countries. A photovoltaic power generation system consists of four basic components. A. Solar cells array. B. Load leveler. C. Storage system. And D. Tracking system. A solar cell array consists of modules, a large number of solar cells, interconnected in series, parallel combinations. A photovoltaic power generating system could be designed to work standalone system, or it can be integrated with the utility system as shown in figure 1.36b. Look at the screen. Solar cells array may be small or large depending upon the need. Convert the solar insulation to useful DC electrical power. The blocking diode ensures that power so generated flow only towards the battery or grid to prevent the discharging of the battery when no solar insulation exists. Cloudy night hours. Battery storage is needed to store the generated power. The function of the inverter converter is to connect the battery bus voltage to AC of the matching voltage and frequency to that of the grid. SAQ10. A. Why are most of the direct energy conversion processes highly efficient? B. For the following cases, state the type of energy conversion and device used. 1. When the coal is burnt. 2. When an electric heater is connected to voltage source. 3. When a ceiling fan is switched on. 1.8 Application of engineering science to energy conversion systems. There are a large number of energy conversion systems where the application of engineering science can be found. Let us discuss some of the important energy conversion systems. 1.8.1 Electrical power generating systems. There are various types of electrical power generating systems based on the nature of the input fuel energy. Some of them are 1. Coal-fired thermal power plant. 2. Diesel power plant. 3. Nuclear power plant. 1. Coal-fired thermal power plant. This system uses coal as fuel. The following thermodynamic cycles are generally used for generation of electrical power. A series of energy conversion that take place in this system is shown in figure 1.37. Look at the screen. 2. Diesel engine power plant. This system makes use of diesel as input fuel for the generation of electrical energy. Type of energy conversion that takes place in each stage for this system is shown in figure 1.38. Look at the screen. 3. Nuclear power plant. This system uses nuclear fuels for the generation of electrical power. The nuclear fuels used in power industry are principally uranium and thorium. The reactor is the heart of the whole plant. It would be seen that in such power plant only the boiler of the conventional steam power plant is replaced by the nuclear reactor and heat exchanger. The type of energy conversion that takes place in each stage of the above system is shown in figure 1.39. Look at the screen. 1.8.2 Transportation systems. We need energy in various forms for our transportation systems. Let us discuss some of the important transportation systems with different stages of energy conversion. 1. Railway transportation system. The railway transportation system makes use of electrical energy, chemical energy contained in coal or diesel. The most essential part of the railway transportation system is either electric, locomotive, steam engine, or diesel engine. The nature of energy conversion that takes place in each stage of these cases are shown in figures 1.40, A, B, C. Look at the screen. 2. Road transportation system. In road transportation, various types of automobiles like bus, truck, car, etc. are used. They use energy of fuels like diesel, petrol and gas, like CNG, etc. Look at the screen. The nature of energy conversion that takes place is shown in figure 1.41. For this type of system. 1.8.3 Tele-communication systems. The purpose of a tele-communication system is to convey or transfer the information from one place to another. Most telecommunication systems operating today employ electrical or electromagnetic media, including light waves, as carriers of signals. These media are harnessed to provide worldwide telecommunication networks. The different stages of the telecommunication with mode of energy conversion is as shown in figure 1.42. Look at the screen. 1.8.4 Solar-assisted water pumping system. Nowadays, photovoltaic system, which makes use of solar energy, can be used in rural areas for pumping water. This type of system is not commercialized yet, but feasibility studies are going on. The type of energy conversion takes place in each stage of the system is shown in figure 1.43. 1.8.5 Integrated energy conversion system. There is a wide application of electrical energy because it can be converted easily into other forms. Let us consider an integrated energy flow system, generally used in household sector as shown in figure 1.44. Look at the screen. 1.8.6 Integrated power generating system for rural areas. In this section, you will get a feel how a combination of photovoltaic and biomass-based power generating system could be utilized to meet the electrical energy needs of rural villages. A life cycle cost for an optimal mix of these technologies is also presented. The main characteristics of selected 4 villages viz. Brahman Kheda, BK, Kundi Kheda, KK, Jar Khedi, JK, and Rudra Kheda, RK, surveyed 100%, are given in table 1.1. These villages situated in the state of Madhya Pradesh were surveyed by Ramchandra et al. To prepare an integrated rural energy plan. Table 1.1. Typical characteristics of 4 villages and availability of fuels, ton per year. Look at the screen. The annual availability of the renewable energy resources, cow dung, agricultural residue and firewood, in these villages has also been listed in Table 1.1. The variation of the resources amongst the 4 villages is because of occupational patterns, agricultural pattern and practices, available irrigation facilities and available tree cover. The monthly variation of consumption of electrical energy in these 4 villages is illustrated in Table 1.2. The lighting load in 2 villages viz. KK and RK is 0, because no connection for lighting were observed during the survey period. In absence of proper metering, the lighting load has been estimated for the remaining 2 villages, and since the accuracy of the estimates is rather low, assumption of constancy is justified. Table 1.2. Monthly variation of electrical energy consumption in 4 villages. Look at the screen. Strategy of optimization of power generating systems. Presently, the main use to which indigenous resources of energy are put to is cooking. Cow dung and agriculture waste compost are also used for agriculture. Any attempt to provide electrical power from Indigenous resources should cause or minimum dislocation to this pattern of usage. Fuel, wood, agricultural waste and some dung, if it cannot be helped. Fertilizer, the preferred application, are usually burnt in traditional cook stoves, chulhas, very low resulting efficiency, -10%, all the dung, which is presently being used for cooking, agriculture waste. And some firewood can be saved by using improved designs of cook stoves, of efficiency 25 to 35%, being popularized by the government. The dung thus saved can be used to produce slurry, which will be a valuable fertilizer, and biogas, which can produce electrical power and can be used for cooking, if in excess. The shortfall between the demand of electrical energy and the energy produced by biogas can be met by photovoltaic generation system and or biomass, agricultural waste, gasifier generator system. Life cycle cost. Life cycle costing technique has been used to yield an optimal mix of photovoltaic, biogas and biomass gasifier generation systems, which corresponds to minimum life cycle cost. The strategy indicated here guarantees some if not more resources for cooking and fertilizer. 5 combinations have been specifically investigated. 1. Stand-alone PV system. 2. Combination of PV and gasifier system. 3. Combination of PV and biogas system. 4. A. Combination of PV, biogas, full utilization and gasifier system. B. Combination of PV, biogas and gasifier, full utilization system. 5. Combustion of gasifier and biogas system. The total life cycle cost of the system corresponding to the above cases have been evaluated. The option having least total life cycle cost is the desired solution. The advantage of life cycle costing technique is that it takes into account the time value of money and converts all future costs into their equivalent present worth. The strategy adopted is described below. Case I. Demand to be met by PV system alone. 1. Monthly generation of electricity from a PV panel of 1 square m. Area is evaluated using the data on solar radiation and ambient temperature. 2. The PV area required to meet the maximum demand, shown in Table 1.2, is evaluated, and then using this area, the generation for each month is evaluated. 3. The battery size corresponds to the lighting load only. 4. Total life cycle cost of the system is evaluated. Case 2. Demand to be met by PV and gasifier-based generation system. 1. Monthly generation of electricity by making full use of biomass. Potential except wood used for cooking, i.e., agricultural waste, is evaluated as shown in Table 1.3. The difference between the demand and the generation by biomass represents the demand, which has to be met by PV. 2 steps, 1 and 2, of case I are repeated. 3. The electricity required to be generated by the gasifier system is evaluated for each month by subtracting PV generated electricity from the monthly demand. 4. The battery size is the difference, if positive, between the lighting load and power generated by the gasifier system. It is given by the following expression. 5. Total life cycle cost of the system is evaluated. Table 1.3. Electricity generation using gasifiers. Look at the screen. Asterisk the fuel, biomass and diesel, consumption rate per kilowatt of power. Productions is 1 to 1.2 kilograms of biomass and 0.8 to 1 liter of diesel. It may be mentioned that the cost data for gasifier generation system in Indian conditions are inadequately available. The cost data are available for Jyoti gasifier. The range of power production varies from 2 kilowatts, model G15, to 40 to 120 kilowatts for model G300. The capital cost for power production is about Rs. 1,200 per kilowatt. Case 3. Demand to be met by PV and biogas-based generation system. 1. Monthly generation of electricity is evaluated by making full use of available dung through biogas route, as shown in Table 1.4. The difference between the demand and the generation by biogas represents the demand, which has to be met by PV. 2. Step 1 and 2 of case I are repeated. 3. The electricity required to be generated by the biogas-based generation system is evaluated for each month by subtracting PV generated electricity from the monthly demand. The remaining biogas is passed on for cooking purposes, if required. 4. Battery size is evaluated as discussed in step IV of case 2. If the lighting load is able to be met by biogas generation, battery size is assumed to be 0. 5. The total life cycle cost of the system is evaluated. Table 1.4. Electricity generation using biogas. Dung used in agricultural operations only. 1 gas yield per kilogram of dung equals 0.0336 cubic meters in winter's month. Generation will be 20% less, while in rainy season the generation will be 5% less. 21 cubic meters per day of biogas at rated efficiency will be 1.54 kilowatt hours per day. The dung used in fertilizer in agricultural operations can be more effectively replaced by slurry from the biogas plants. Case 4. Demand to be met by PV, biogas and biogas-based generation systems. 1. Monthly generation of electricity is evaluated by making full use of biomass potential, step 1, of case 2, and dung, step 1, of case 3. 2. Total monthly generation by biomass and biogas is then evaluated. The difference between the demand and the combined generation by biomass and biogas represents the demand, which has to be met by PV. 3. Steps 1 and 2 of case I area repeated. 4. The generation required from biomass and biogas are then evaluated, as discussed in step E of case 2 and case 3. Excess biogas is passed for cooking. 5. Battery size is evaluated as discussed in step 4 of case 3. 6. Total life cycle cost of the system is evaluated. 2 scenarios have been developed for this case. In one scenario, the demand is met by PV and biogas generation system, full potential, and remaining demand is met by gasifier generation system. In the second scenario, the demand is met by PV and gasifier generation system, full potential, and remaining demand is met by biogas generation system. Case V. Demand to be met by biogas and gasifier generation system. 1. Monthly generation of electricity by biogas, making full use of dung potential, is evaluated. 2. The generation required from gasifier is evaluated by subtracting generation from biogas from the demand for each month. 3. The battery size corresponds to the lighting load only. If the light load is able to be met by the combined generation of biomass and biogas generation system, the battery size is taken as 0. NCE biogas is not sold in any of these villages. PW, BSC, is assumed to be 0. If, however, the biogas cost released for cooking is included in the analysis, it will reduce the life cycle cost and hence will further improve its viability as compared to other options. Table 1.5. Characteristics and total life cycle cost of optimal electrical energy system for meeting the entire electrical energy demand. Look at the screen. PVB equals PV plus biogas can meet the demand and hence gasifier is not required. PVG equals PV plus gasifier can meet the demand and hence biogas is not required. GNR equals gasifier not required because biomass is not available. NP equals not possible. Table 1.61. Data used in computing total life cycle cost. Look at the screen. The characteristics and total life cycle cost of optimal combinations, case 1 to 6, for the 4 villages are presented in table 1.5. The numerical values of various parameters used in the calculations are given in table 1.6. It is seen that electrical power generation by biogas, dung, and gasifier, agricultural waste, is less expensive than that by photovoltaics, but these resources are not enough in amount to meet the total demand, hence photovoltaics is an essential component of an optimal mix. From table 1.5 and table 1.2, the unit cost of electrical energy in the 4 villages, when an optimal mix of technologies is implemented, worked out to be as 8.8 per kilowatt hour for BK, 4 rupees and 50 paise per kilowatt hour for KK, 8 rupees and 40 paise per kilowatt hour for JK and 2 rupees and 20 paise per kilowatt hour for RK. The variation in widely differing conditions is within a factor of 4. The higher costs corresponds to cases where relatively less indigenous fuels, dung and agricultural waste are available for generation of power, and a greater share of demand is met by relatively expensive photovoltaic demand. The indigenous sources of fuel, dung and agricultural waste for final production of electrical energy are not able to fully meet the demand. The increased use of fuel wood leading to deforestation is out of question from the environmental point of view. With increasing demand of electrical energy for development and welfare, photovoltaic appears to be the only decentralized alternative to provide the additional energy. It is seen that the optimal combination of technologies, corresponding to a decentralized system to meet the electrical energy demand of a typical village, without disturbing the forest cover, cooking resources and fertilizer application is 1. Meeting as much demand as possible by utilization of available dung in biogas generators, and 2. Meeting the rest by photovoltaic generators and biomass gasifier generators, using agricultural waste. 1.9 SUMMRY. Multi-stage energy conversion and direct energy conversion are two basic modes of energy conversion. Generator and motor are two important devices of the electromechanical energy conversion process. DC generators are used to convert mechanical energy into direct voltage and current. AC generators convert mechanical energy into alternating energy. DC motors are used to convert direct electrical energy into mechanical energy to drive mechanical load. AC motors convert alternating electrical energy into mechanical energy to drive mechanical load. Electromechanical energy conversion systems are widely used. For the case of direct energy conversion, electro-chemical system has the highest conversion efficiency, almost 100%. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.